Hi, today's lecture or video lesson or whatever you want to call it is going to have two parts. In this first part, I'm going to give you some background and talk a little about some of the different kinds of exponential and logarithmic models there are, the five types that are discussed in this section of the book. And a lot of what I'm going to say in this first part, I'm not going to test you on or make you do anything with, but it's stuff that I want you to be aware about, both in general and in particular right now with the coronavirus pandemic that we're in the middle of. A lot of this is relevant to what's going on. So when you see things about the infection rates and how the virus is spreading and the mathematical models that are used to describe that and flattening the curve and all that sort of thing, the kinds of models that are being used there relate to the kinds of things that they're talking about in this chapter. So, first of all, exponential growth and exponential decay models. So that's where you have a function of the form y equals some number times e to some number times x. And that number could be positive, which is where you get exponential growth, or it could be negative, which is where you get exponential decay. And we will talk more about those later on. In part 2 of this video lesson, we will be working through some examples involving these kinds of models. And we won't really do anything with these other kinds, but like I said, I want you to be aware of them and just be exposed to them. So an exponential growth model, here's one particular example. If I wrote y equals 100 times e to the 0.05x, that would be an example of an exponential growth model. Here the number a is 100 and the number b is 0.05, and the graph looks like this. At first it looks pretty flat, but before too long it starts shooting way up. And the thing about these exponential growth models is that the rate of growth, how fast this is going up, is proportional to the size of the function. The more there is, the faster it grows. Now, quick side note, other exponential functions with other bases, like instead of e to the something, if you got some other number, 2 to the something, or 3 to the something, or something like that, they fall into this category as well because they can be rewritten to look exactly like this. I could take y equals 2 to the x, and that would be the same as e to the ln of 2 to the x, because e and ln undo one another. And then the ln of 2 to the x power is equivalent to x times the ln of 2 by one of those properties of logarithms. So I can write it as y equals, here the a would just be 1 times e to the b would be the number ln of 2 times x. So this does count as one of these exponential growth models of the form y equals a times e to the bx. But like I was saying, with this kind of model, the more there is, the faster it grows. And so when you have something like the spread of an infection, it often follows this kind of pattern, at least at the beginning. The more people are infected, the faster the infection spreads to yet other people. And that's because if there are only a few people who have an infection, there aren't very many people that you could catch it from. But as more and more people get infected, there are more and more opportunities for an uninfected person to be exposed to the infection and catch it themselves. And so the more people have it, the faster it spreads. And here's a graph I found online about the total number of cases of coronavirus infection over the period of time from sometime in January to sometime in April. And that curve does look an awful lot like those exponential growth curves. Now, it can't keep going up indefinitely. It can't follow this pattern forever, because if it did, eventually this curve would get up until it was higher than the overall population of the whole world. So there is a limit to how many people could be infected. So another kind of model is more accurate in the long run, and that's what's called a logistic growth model. A logistic curve is something that looks like this, where at first it looks like one of those exponential growth curves, but at some point it starts to, the rate of growth starts to slow and the curve starts to level off. So the kind of equation that gives you that kind of a graph is where you have y equals some number over 1 plus some number times e to some negative number times x. So here are a few specific examples. If I write y equals 2 over 1 minus e to the negative 3x, the graph looks like this. If I write y equals 2 over 1 minus 4 times e to the negative 6x, same basic shape, just changed a few of the details. Y equals 3 over 1 minus 2 times e to the negative 1.5x. They have the same basic shape, where kind of goes up and then levels off. And that's the kind of situation you have when there is some limiting factor, some limit to how much something can grow. There's a limit to how many people can get infected. And in the long run, the how fast the infection spreads is going to depend not only on how many people are infected, but also on how many people are not infected yet. Because if almost everybody has already been exposed to the infection, then it can't grow much further, because there aren't that many new people who could still become infected. So this kind of model often describes the situation where something is spreading in a limited population. It describes situations like if there is a lake with fish in the lake and there's only so much room, or the lake can only support so many fish. If you introduce a few fish into the lake, at first the population might grow, but it won't grow indefinitely. Eventually it's going to sort of level off and reach the lake's carrying capacity, where there isn't room for any more fish. This kind of model is used to describe a situation where there's some rumor or piece of news that gets spread from person to person, and at first only a few people know about it, but they tell other people, and those people tell other people, and eventually lots of people know. Or there's a funny video that goes viral and spreads from person to person as people share it with their friends. And at first, the more people know about it, the faster it's going to spread, because the more people know about it, the more people they tell, and then those people tell more people. But eventually, the number of people who haven't heard about it yet or haven't seen it yet is going to go down. And so there aren't going to be as many people that it could get spread to. And so that's going to limit the growth rate and make it eventually level off. And then Gaussian models, that's where you have an equation of the form y equals some number times e to the, maybe you got negative x squared, maybe it's shifted so it's not just x, but x minus a number, and it might be divided by some other number. And this gives you a mound shape or bell-shaped curve that's nice and symmetrical, has like a lump or a hump where it goes up and comes back down. when you see those graphs and where people talk about flattening the curve that's usually pictured is some variation on this, and flattening it makes it not go up as high but goes out further. And if you've ever taken a statistics class, you have worked with curves like this when you were talking about things like normal curves and normal distributions. So that's all I'm going to say about that. The book talks about that a little in this section. You can read that if you want, but like I said, the stuff about the logistic growth models and the Gaussian models and things like that are good to be aware of, but we're not really going to do anything with them. I'm not going to test you on them or make you work any problems with them really or anything like that. So that's it for part 1 of today's video lesson. Now in part 2, when we start up there, we're going to work through some actual examples where we are working with those exponential growth models. We're going to do some word problems, work through some examples where we use our formulas to actually calculate some things and answer some questions. So see you in part 2.